Recording.
Hello, we're Group 8. We're presenting imaging artifacts. Next slide, please. Synopsis. Our project focuses on understanding how motion creates artifacts in MRI images and how these distortions arise from the way K-space is acquired. MRI collects data line by line over time. Any patient movement, like breathing, swallowing, or sudden head shifts, causes mismatches between lines of K-space. These mismatches generate two major issues: ghosting, where repeated copies of anatomy appear along the face encoding direction, and blurring, where edges lose sharpness. To study this, we stimulated MRI acquisition using a T256 into 256 modified step-Logan phantom and introduced two types of motions: rigid translational shifts similar to sudden movements and phase modulation, which mimic rhythmic breathing. We then reconstructed the corrupted K-space using an inverse FFT. The results clearly showed that translational motion produces strong ghosting, while phase modulation adds wave-like blurring, and combining both leads to highly distorted images. We also quantify the degradation using metrics like MSE and PSNR, which worsened significantly as motion amplitude increased, demonstrating MRI's extreme sensitivity to even small movements. Finally, we reviewed real-world correction methods such as navigator echoes, gating, and faster sequences like propeller. Overall, our project highlights why motion is the most common real-world MRI challenge and emphasizes the importance of both stimulation and correction strategies in improving clinical image quality. Next slide, please. Why imaging artifacts matter. You'll notice that MRI is extremely sensitive to motion. Even small movements like breathing or slight head motion corrupt individual lines of K-space during acquisition. When this happens, the final reconstructed image shows ghosting or blurring like the example shown here. This is a major clinical issue because artifacts can mimic a disease, like making a normal structure look like a lesion or hide behind pathology completely. Motion is also most common artifact in real-world MRI, especially in neuroscans where people naturally move. Because of this, our project specifically focuses on modeling motion in K-space and showing how these artifacts form. Understanding this helps us connect the physics of acquisition with the clinical consequences. Next slide.
We'll now look at the underlying mechanism behind motion artifacts. MRI collects case-based data over time, one line at a time. That means that each line is acquired at a slightly different moment in time. If the patient moves during the scan, some of those lines now represent the anatomy in a different position than the others. This creates time-dependent phase errors. Looking at the formula on the slide, it describes how MRI forms case-based data. The signal at each case-based point is the Fourier transform of the object, but the important term to note is the y of t. If the object moves during scanning, this position changes over time. That change introduces a different phase into different case-based lines, which creates a phase mismatch. When we reconstruct the image, the result is ghosting, blurring, or multiple repeated copies of anatomy. Next slide, please. MRI images can be affected by several different types of artifacts. Besides motion artifact, which we'll dive into later, there are artifacts like Gibbs ringing, which happens when sharp edges aren't finely sampled enough. This effect can be seen in Figure 4. Another type of artifact is susceptibility artifacts, which can be seen in Figure 5. This artifact comes from metal or strong air tissue boundaries. Shown here is an example of metal in the mouth cavity. Aliasing is another type of artifact which occurs when the field of view is undersampled and anatomy wraps into the image, and this is seen in Figure 6. All of these can impact image quality, but motion artifacts are by far the most common in real clinical scans. They're also the hardest to control because patients naturally breathe, swallow, and slightly move during long acquisition times. That's why our project focuses specifically on understanding and simulating motion artifacts. Next slide, please. Now, looking more at motion artifacts, motion corrupts K-space because it makes different phase encoding lines inconsistent with one another. When those lines no longer match, the reconstructed image shows ghosting in the phase encoding direction or overall blurring. In real clinical scans, this kind of motion comes from normal things like breathing, swallowing, small head shifts, twitches, or tremors. These types of movement are nearly always present, and even very small movements can distort the image. Clinically, motion artifacts are important because they can hide subtle lesions, distort anatomy, or even mimic the appearance of disease. This often leads to repeat scans and reduced diagnostic confidence, which is why understanding and correcting motion artifact is so crucial. Next slide, please.
For our motion artifact simulation, we used a modified step-Logan phantom over a 256 by 256 image matrix, and we acquired its K-space. These can be seen in figure 9. To acquire this K-space, we used 2D Cartesian K-space sampling, which is basically going through the K-space line by line. Each line is acquired at a different time in a sequential order. This method is most commonly used in clinical MRI sequences, as it is generally robust to noise and provides a fast reconstruction. After, after doing so, we corrupted the K-space using two different kinds of artifacts. We then reconstructed the image using inverse fast Fourier transform. The two different kinds of artifacts that we added were rigid body translational motion, where we essentially shifted the pixels of the original image. This is meant to represent sudden movements or patient motion. The second artifact we added was phase modulation, where we multiplied each K-space line by different complex phase term. This is meant to represent a steady breathing motion throughout the duration of the scan. Here is a graphical representation of the two different kinds of artifacts that we added. So in the translational motion, we shifted the pixels of the image sinusoidally over the duration of the scan. And then similarly for the phase modulation, we added a complex phase term for each ky point by going from 0 to 256, as that's how many lines were in the original image. When we look at the K-space corruption from artifacts, we notice that both these artifacts affected the K-space a little bit differently. So for the translational motion, you see distortions along the phase encoding directions, corrupted lines, and discontinuity. Similarly, for the phase modulation, you see corrupted lines along with phase offsets and change in spacing. In both these cases, the corruption is more towards the periphery of the K-space and doesn't really affect the center as much. When we reconstruct the image, we see two different effects happening. For a rigid translation, we see bright ghosts appearing in the phase encoding direction due to the discontinuities along the K-space line. And for the phase modulation artifact, we see blurring caused by steady repetitive movement throughout the scan. For the phase modulation especially, you can still make out the general features of the phantom as the center of K-space wasn't affected as much. And when we combine those two artifacts and reconstruct it to a single image, we get an image that's extremely distorted. The corruption of the reconstructed image depends on a number of variables. We specifically focus on translational motion and change the amplitude of the motion to see how it would affect the reconstructed image. We essentially increase the distance the pixels were being shifted. We started with an initial amplitude of 5 and increased to 7.5 and 10. What we saw were more pronounced K-space distortions, and as the amplitude increased, we noticed that the changes in K-space were more towards the center, not just the periphery. This resulted in a lot more prominent ghosting effect in the reconstructed image and more noise. This just goes to show how sensitive MRI systems can be to motion artifact. With even a small change in the translation amplitude, we got such a big difference. We also did a quantitative comparison of all the different images that we reconstructed. We did this by using three different metrics: the mean square error, the peak signal to noise ratio, and the ghost to signal ratio. We could essentially compare all our reconstructions with the ground truth image that we originally had. For the PSNR and GSR, it's important to note that the higher the value, the better. So going from a translational amplitude of 2 to 10 pixels, we notice a 255% increase in the mean square error and a peak signal to noise ratio that was 3.5 smaller as the values are in decibels. In figure 17 and 18, you can essentially see a graphical trend of how the image quality degraded and noise increased.
How to reduce or correct motion artifacts. Now that we've shown how motion corrupts K-space and produces ghosting, we'll briefly look at how these artifacts can be reduced in practice. First, we have post-processing motion correction algorithms which cleans up the image after acquisition by estimating and compensating for phase inconsistencies. Navigator-based methods add small extra scans during the sequence to detect motion and correct it retrospectively. In contrast, prospective motion correction works in real time. The scanner tracks the patient's head movements and actively updates gradients and RF pulses to correct for motion as it happens. Clinically, we also reduce motion with breath holds, sedation in pediatric scans, and gating, which synchronizes the scan with the patient's breathing or heartbeat. Finally, using faster or motion rebus sequences like EPI, radio trajectories, or propeller helps minimizes the time where motion can occur. These strategies connect our stimulation back to real MRI workflows. Next slide, please. Some limitations and approximations. In our stimulation, we make several approximations that simplify the real MRI acquisition. First, the motion we model is idealized. We only apply rigid translations and phase shifts to specific case baselines. Actual patient motion is much more complex and often non rigid, especially in areas affected by breathing or swallowing. Second, we assume uniform timing between phase encoding lines, which makes it easier to insert motion at control points. In practice, scan timings can vary across sequences. We also use a single phantom image, so our images don't capture anatomical diversity. Our simulation is limited to Cartesian sampling, whereas clinical scans may use radial, propeller, or spiral trajectories that respond differently to motion. Finally, the stimulation does not include hardware noise, physiological fluctuations, or gradient imperfections, all of which contribute to real MRI artifacts. So, while our results demonstrate the core mechanisms of motion ghosting, they represent a simplified version of what occurs in practice. Next slide, please. Here are our references, and thank you very much.